In this talk, I'm going to assume that the universe is expanding and that it is expanding forever and that it is expanding in an accelerated way and that it is expanding in a way such that this quantity is finite. So assume, for example, the Friedman, Lemaitre, Robertson-Walker metric with zero curvature. And if you put ds equals 0 to find how long light travels from now to eternity, from you to wherever you want, you have to put it to 0 to integrate dr. And a, the scale factor, is e to the ht. 3h squared is the cosmological constant. And so you see the result is 1 divided by h times a of t. So the maximum comoving distance you can reach with a signal of light is finite, not only, it's finite, but it is decreasing exponentially to 0. So if you imagine the universe as planet Earth, it's not, but let's imagine it for a moment like that, then the comoving coordinates are longitude and latitude. So we are in Shanghai, and let's say today we can reach Beijing and beyond Beijing by sending a signal of light from now to eternity. But in the future, we will not be able to reach Beijing, maybe, but just Nanjing. And in the future, we will not be able to reach beyond the suburbs of Shanghai. And in another future, we will not be able to reach the walls of this room. And in another future, we will be not able to reach our nose, and so on and so forth. So I'm assuming this kind of situation. And so a possible state of the universe is the one where you dilute all the elementary particles, the stable elementary particles, if you want, so that their relative distances are all exceeding this quantity. If you are in such a state, which I call total dilution, which is a possible state of the universe, then there is no physical communication. There won't be any physical communication for eternity among any particles. And in particular, you cannot even say they are particles because they are only wave functions. So they cannot even collapse. They cannot meet an observer, a macroscopic object, a detector, something that makes them collapse. So I call it also cosmic virtuality, or eternal entanglement, because they will be entangled from the past, and you won't have any chance to disentangle them by means of a wave function collapse. So I kind of like this kind of possibility as the death of the universe. So my question is, will the universe evolve into such a final state no matter the initial conditions? So we will ask this question. First, I will start with the motivation, because the motivation from this is kind of philosophical, but also physical. And it starts from the role of virtuality everywhere in the theory of quanta. Virtuality has zero role in classical physics, but in quantum mechanics, you know that you have to interpolate between two successive measurements, wave function collapses, by means of a wave function, an imaginary, a complex wave function, something that is not real, something that we can call virtual. And entanglement is a striking manifestation of the virtual nature of this. In the meantime, so you have a before. Before is physical preparation of a state. You have an output, and after, that's the final result. And you have something in the meantime. And in the meantime, it means virtual. Then, of course, you can move to quantum field theory, and quantum field theory, you also have a major role of virtuality, because the propagator has an on-shell contribution, and you call it shell precisely because it is just a shell, and everything else is virtual. And then there is another thing, which is the one that inspired this idea, which comes from a theory of quantum gravity that I proposed some years ago, which is based on the notion of purely virtual particles. And now I describe that. And that is a way to formulate quantum gravity in a very conservative way, stemming from high energy physics. And so it's the minimal thing you can do without destroying too much, let's say, and importing all the knowledge from the quantization of the standard model. It's an extension of the Starobinsky model, and it's also predictive. And this is the prediction for the tensor to scalar ratio. There is this tiny window, and the upper bound is the Starobinsky prediction, and the lower bound is something that comes from the nature of these particular purely virtual particles. Purely virtual particles are particles that more or less encompass the idea I want as the end of the universe. Those particles are never on shell. How can you define something that's never on shell? So first of all, the theory is quadratic gravity, but it is quadratic gravity in a particular way. So start from this classical Lagrangian, Starobinsky, which is this one, plus y squared, and you have the inflaton mass and another mass here. This is by no means the classical Lagrangian of my theory, because this theory is not acceptable, not even classically acceptable. So I do not want to claim that this is an acceptable classical theory. And I think that anybody who speaks about quadratic gravity should address this problem, because that theory not only has ghosts if it is quantized as you normally do, but it is just not acceptable classically. So you have to address the problem of the classical limit. We will do something completely different. We deal with the unitarity issue by defining new non-time ordered correlation functions and diagrams, and those will allow us to slice out all the on-shell contributions of this extra term, which otherwise would be a ghost. On-shell contributions are eliminated from outside and inside the diagrams. You don't have them. So you treat them as Faddeev-Popov ghosts, basically, and you are able to show without the help of a gauge symmetry that you can remove them from everywhere, outside and inside the correlation functions, without the help of a symmetry. There is a price to pay that you do not pay with Faddeev-Popov, and that is a violation of microcausality. Actually, I do not want to emphasize the notion of causality too much, because I think that it is a very fishy notion in physics. And so let's say you do not have chronological order. You do not have past, present, and future for small intervals of time. And how small should they be? 1 divided by the mass that you find here. 10 to the minus 36 seconds. So there is no notion of time, chronological order. This is what the theory predicts. Below 10 to the minus 36 seconds. And you can ask, what are the shortest intervals of time we can measure? 10 to the minus 18. So this is in contradiction with nothing. The bubble diagram was explained by Leonardo 2 days ago, so I just asked him to give me his slide, just to show how to compute diagrams in this method. This is 2 propagators. You integrate on the energy with the residues. This is an algebraic operation. Then you use this decomposition, and you throw out all the deltas that involve any frequency associated with a particle that you want to render purely virtual. That's it. You can do it in every diagram, and you can show that this is consistent with renormalizability and unitarity. As simple as that. And instead of taking Feynman diagrams and subtracting things, you can add other diagrams that subtract what's wrong in the Feynman diagrams, and those are non-T order diagrams. And that means that if you have, for example, a triangle, you have to add diagrams where you cut lines in all possible ways with all numbers of cuts. A cut propagator is on shell, just the on-shell part, and you have to do it with certain specified coefficients given by a certain formula so as to subtract the unwanted terms. And then I want to make a comment here, because in recent papers I studied the generalization of this construction to finite time QFT, because I do not want to emphasize on-shellness too much. On-shell is something we use when we talk about scattering, but if you have an unstable particle like the muon, that's not on-shell. If you have a resonance, that's not on-shell. If you have finite time QFT, there is nothing on-shell. So you have to show that this construction does not rely on the notion of being on-shell or being virtual in the sense we normally use for scattering processes, and that is okay, you can do it, but I won't comment too much on this. Anyway, the prediction of this theory is the Starobinsky prediction multiplied by this factor, and the nature of these purely virtual particles in a curved background, skip the details, put a bound on this mass. This mass can be derived from the scalar spectra, 10 to the 13 GeV, and this must be bound like this. So the window is as large as this. So basically, Lightbird in 10 years will be able to reach this window, but very probably it will just confirm the Starobinsky prediction, because the error will be not small enough. It depends. It could be small enough to distinguish a point in between these two extrema and this Starobinsky point. So depends. But anyway, just to show you that the Starobinsky model basically got it right. This is my claim. 1980. So you can imagine this theory, the Starobinsky theory, as the four-fermion theory of Fermi for the weak interaction with respect to the standard model. And the four-Fermi theory was predictive, of course, for many cases, and this is one in the analogy we are talking about. So this you can do for every diagram. I want to also make a comment and compare these observations with asymptotically local quantum field theory. You have heard about it 2 days ago by Modesto, Calcagni, and Rachbal. They call them non-local theories or weakly non-local, but I suggested to them to call them in a more cool way. Asymptotically local is much nicer, I think. And what are these theories like? They have propagators and vertices of a non-local theory, but they are such that those tend to propagators and vertices of a local theory when momenta exceed some scale. So they are asymptotically local theories. Basically, on shell, the propagators have the same degrees of freedom. It could be graviton and inflaton, because the third one is purely virtual for me. The other two could be physical, or could only the graviton be physical, because you can render the inflaton purely virtual as well. But the point is that you have different virtual sectors, and you have quantitatively different predictions. Although also, in their case, normalizability and unitarity are okay, microcausality is also violated in a quantitatively different way. The feature of these theories is that there are infinitely many ways to extend a local theory to a non-local one. So large family, infinite family of theories, and you need a selection principle to identify the correct asymptotically local quantum gravity. In the case of the theory I was describing, my own, instead, the theory is unique because it is the unique one which is strictly renormalizable. So let's come from the general inspiration for believing that maybe the notion of virtuality will be so intimate in physics that the whole universe will be de facto one day be purely virtual, which means that you have a total dilution, so that even physical particles which have on-shell contributions would be like purely virtual particles, because those on-shell contributions will never be able to matter from some time onwards and for eternity. It's kind of philosophical idea, but I like it, so why not? Let's see. Let's reconsider everything by incorporating the expansion of the universe and see if the expansion of the universe is enough, for example, to expand stars, white dwarfs, neutron stars or not. Okay, kind of interesting. First of all, let me tell you about our universe. We are, of course, arranged in planets and then stars, and stars are grouped into galaxies, and then galaxies are grouped into clusters. The Milky Way, Andromeda, and Magellan nubes make the local group, which is our cluster. Inside the cluster, you do not have expansion, okay? And you have expansion among the clusters. So clusters are getting farther and farther as time passes by. So you have this, these are galaxies, but imagine that these are clusters, not galaxies. And the expansion of the universe in a homogeneous distribution has the following effect, that a cluster here, our local group, for example, is attracted by a cluster there, but there is another one, an opposing one, which attracts us in the opposing direction. So basically, the gravitational force is balanced, and then expansion prevails, and those become more distant as long as time passes. And then you have that they reach, at the cluster level, we already expect that, under the assumptions I made at the beginning, that you reach the state of total dilution, where no cluster will ever be able again to send signals of light and reach any other cluster for eternity. The question is homogeneity? First question is homogeneity necessary to have this kind of evolution? I want to show you that this is not necessary. By giving you a classical system, an exact classical system that evolves towards this state of total dilution without homogeneity. And this comes from, well, first of all, as a warm-up, let me consider the black hole, Schwarzschild black hole in y coordinate, isotropic coordinates. And this is kind of nice because in these coordinates, it's very, very simple to incorporate the cosmological constant. Just multiply r by the scale factor, and you can check that this metric satisfies the Einstein equation with a cosmological constant, just like this. And I thought I had discovered something beautiful, but this has been discovered many, many decades ago. This is the so-called McVitie metric. Well, if you want to focus on the Newtonian approximation, you can have an arbitrary distribution of black holes in positions Ri in co-moving coordinates, and then you can see that to the lowest order, the scale factor to incorporate the cosmological constant multiplies the whole potential. So the black holes remain at fixed distances in co-moving coordinates, which means that they will, in static coordinates, they will move apart. They will separate and dilute. But this is just an approximate solution, so let me not focus too much on this. It's just a warm-up. Focus on this, because there is a very nice metric that has been known since 1947, and this is the Majumdar-Papapetrov system, which is an exact solution with an arbitrary distribution of black holes. This is an exact solution. Phi is the same as before. Laplacian of phi is 0. This is an exact solution with an electromagnetic potential like this of the Einstein-Maxwell equations. And even in this case, if you put some A of t multiplying phi in all places, you find that miraculously the Einstein-Maxwell equations with the cosmological constant are solved. And again, I thought I had discovered something beautiful, but then I found that people had already derived this metric in the 90s. And these are Castor and Trossen. But the nice thing of this is that you see that the expansion of the universe multiplies the potential overall, and here there is no discussion as before. It's not approximate like the Newtonian approximation. This is true, and so the expansion of the universe has no effect on the relative positions in co-moving coordinates of these black holes, which means that eventually they will not be able to send any physical signal from one another. So they will be fixed in moving coordinates, and the maximal distance traveled by light from any of them is shrinking to 0. And if you are not convinced, just study the geodesic equations with the Maxwell correction, and you will find that staying in one fixed position in moving coordinates is indeed a geodesic. So if you have a distribution of these kind of black holes, and you put a new one, it will not fill any of the existing ones, and it will stay there. So what is the reason why this system works? It's that the gravitational attraction is perfectly balanced by the electrostatic repulsion. So again, let me stress that I have a electromagnetic potential. You see that you have only electrostatics here, and these are charged black holes, and the charge and the mass have to be related by a certain condition, which is here. And when the mass and the charge is satisfy this condition, the electrostatic repulsion compensates the gravitational force, and then you have that compensating the gravitational force with the electrostatic repulsion, even if you do not have homogeneity, but just an arbitrary distribution of black holes, they will dilute forever due to the expansion of the universe.
So all black holes have the same charge?
They can have different charges, but all...
I mean the same positive or negative?
It has to be positive because it has to be repulsive, but it has to be related to its own mass. Then you can ask, is this a realistic condition? Absolutely not. There is no elementary particle satisfying this, but if you could build macroscopic objects that are almost neutral with just a tiny difference of positive and negative charges so as to satisfy this. But this is not the universe. It's a model that shows that some things are possible. So I asked myself, maybe the expansion prevails anytime the gravitational force is compensated by an opposing one. So let's consider realistic objects like stars, white dwarfs, black dwarfs, neutron stars, and later black holes. But black holes are not so important here. So in 5 billion years, let me see how much time I have. Okay. In 5 billion years, our sun will explode into a red giant, and over the course of millions of years after that, it will shed its outer layers and transform into a white dwarf. What is a white dwarf? A white dwarf is a star where the gravitational force cannot collapse the star any longer because it is balanced by an opposing force, and that is the degeneracy pressure due to the fact that you have electrons, fermions, and fermions have to fill the Fermi surface, okay, due to the degeneracy pressure, so-called, of fermions. And so the star, the sun will end into a white dwarf. And is that stable forever, for eternity? That's the question. Well, first of all, it is white, so it's not completely stable because it radiates. There is some temperature, but eventually there is speculation that it will radiate everything it can radiate and become what we could call black dwarf. We know of many white dwarfs in the universe. We do not know of any black dwarf because it takes too long and there hasn't been enough time in the past to reach that state. But the black dwarf is considered completely stable. Okay, but these things are studied, and the neutron star is the same with larger masses. Protons and neutrons form, protons and electrons form neutrons, a very compact star. And if you have even larger masses, you have a black hole. So you can have black holes, neutron stars, or white dwarfs. But normally, these objects are studied without incorporating the expansion of the universe because the expansion of the universe today is negligible. So my question was, okay, is it truly negligible? Because maybe since I want to integrate the effect from now to eternity, maybe it could contribute. And so I went through the study of neutron stars and white dwarfs in incorporating the expansion of the universe. So you start from a generic isotropic metric like this, where you leave unknown two functions. U is a rescaled co-moving radius by A of t. A of t is the usual expression. You study the Lagrangian, the geodesics, basically, so you have the gravitational force, but then you have to switch to fluids, because this is a Fermi gas, and it's important to have the repulsion, the so-called, given by the degeneracy pressure, and you have to study the fluid equation, where you have two contributions. One is the gravitational force coming from the geodesics, and the other one is the gradient of the pressure plus what you need to make everything general covariant, but anyway, some force due to the pressure. But the hypothetical equilibrium, does it exist or not, should be searched for not in co-moving coordinates, but in static coordinates. And these are those that you obtain by rescaling the co-moving coordinates by A of t. Because remember at the beginning that I told you that the maximal co-moving distance light can travel from now to eternity is this. But if you multiply distances by A of t, this A of t goes there, so it's just 1 over h, static. In these coordinates, the universe expands, and the distance light can travel is fixed. So Beijing and Shanghai will fall apart, and the distance light can travel in between stays fixed, and eventually we won't be able to communicate with Beijing any longer. So you switch, this is just a change of coordinates, you switch to those coordinates, and then you find that the equation of motion has an extra contribution. Gravitational force, in the fluid we will have the pressure force, not here because this is just a particle, and this. What is this? This is a centrifugal force due to the expansion. For example, if you want to include the expansion and search for the circular orbits, you find this equation, in the Newton approximation you find this equation, you see that the angular velocity of circular orbits is corrected by h squared. So h plays the role of an angular velocity. So the expansion of the universe is like a centrifugal force in this approach. So now we have three forces when we go to a fluid, and which is the Fermi gas of a white dwarf. And the fluid equation has the force, total force, which is the sum of three contributions. One is the centrifugal force, one is the gravitational force, and then the last one is the pressure. And then you can go through the solution, but I skipped the details. There are some parts of the equations that you can even integrate exactly, and that's kind of nice. And the other part you can work out by expansion in powers of the Newton constant, and so on and so forth. You can go to the solution and recover the usual equilibrium situation. I just described to you what is the usual equilibrium solution without the expansion of the universe for a white dwarf. Basically, you have a density that decreases with the radius up to a maximum radius, because the star has a maximum radius. And believe it or not, this is kind of nice to me because I come from high energy physics or quantum mechanics, where something that's zero somewhere normally is always zero, everywhere zero, but outside the star, the solution is identically zero. At the border, the solution approaches zero. At the border, the derivative of solution 3 over 2 becomes 1 over 2. The derivative of the solution approaches zero as well. And this is consistent with the fact that the star does not lose any particles from its border, because the derivative of the density is the pressure, and the pressure equals to zero at the border. So that's fine. That's a nice equation that's non-linear. It's not like a Schrödinger equation where there's a wave function that's zero in an open set, unless it is singular. It's everywhere zero. Okay. But there is a nice, interesting thing that you can ask. Okay, so what? Now you have found what? I found a solution of equilibrium of a white dwarf by incorporating the expansion of the universe in static coordinates, where the maximum distance traveled by light is 1/h, which means that there is an equilibrium configuration pretty much like this circular orbit for one particle, which means this system is indifferent, totally indifferent to the expansion of the universe. So in circular orbits, you have u equal constant, but u is r times a. The constant is compensating, so it's like saying that the universe expands, but the circular orbit shrinks, and so it stays the same. You have to spend a minute to figure it out, but that's it. So if you find an equilibrium solution, and we found an equilibrium solution, this means that the expansion of the universe will not be able to destroy a white dwarf or a black dwarf. This stays there forever. Well, actually, you have to check the properties of these solutions, because there are some things that are a little bit tricky. For example, you have you have fractional powers of something that could be negative. So you enter into some more details, okay? And you check that indeed you have to put a condition to find the solution, and the condition is actually quite reasonable, and the condition is this. So you have a centrifugal force and you have a gravitational force. You have to check that the centrifugal force at the border of the star is smaller than the gravitational force at the border of the star. Because if the centrifugal force is larger than the gravitational force, it wins. And the star cannot exist. So you have an inequality that you have to satisfy, because you are compensating the gravitational force with the degeneracy pressure, okay, but you also have the expansion of the universe, which is like a centrifugal force. But if the centrifugal force is already bigger than the gravitational force, there is no hope, and there is no possibility to build a neutron or star or white dwarf. But then you put the numbers inside and you find that, as one expects, the value of the Hubble parameter today makes it impossible to violate this condition. So basically the expansion of the universe is truly negligible. But during inflation, it was the opposite. Because during inflation, the Hubble constant was 10 to the 55 times larger than today, and so the situation is reversed. So today, this ratio, this gravity divided by expansion is huge. You are in the condition to find an equilibrium, but during inflation, it was negligible. So you are in the opposite situation, which means that, as you know, there could not exist any star during inflation. We know that because it was before the formation of stars. But this tells you that even if you wanted to build a star at that time, it would have been impossible because of this. The expansion would have destroyed it completely. And even elementary particles, probably, and indeed no elementary particles existed during inflation. So this is kind of nice. But what you, so now I conclude, I think that I'm about in time, yeah? What is the lesson we learn from this about the fate of the universe? So basically, we have found that some systems, even if they are not homogeneous, can reach the state I'm advocating for as the death of the universe, or the state of total dilution, in a classical way. But those are not realistic systems. Realistic systems where the gravitational force is balanced by a degeneracy pressure of a fluid, because you have a fluid that can adapt itself to many situations, it compensates it compensates the expansion and makes it irrelevant, basically, and you have stability. But is this stability forever? And the final thought I want to leave you with is that no, because this is classical, and then to get out of this, you have to advocate this time as well the theory of quanta, because you know that in quantum theory nothing is stable. Nothing can be stable for eternity. Black holes, for example, evaporate. What is evaporation? This is a way of balancing the gravitational force. And there is speculation that everything can evaporate because by means of the Schwinger pair production mechanism, you can generate produce pairs even from a field. And so if you have a black dwarf that generates a gravitational field, and the gravitational field in a long time produces pairs, and some of those pairs are diluted, then even the black dwarf evaporates. So I'm going to study this thing right now in detail to prove the statement, but I think that this will be the final statement, namely that nothing is really stable in a quantum world, and so eventually the total dilution state will be necessarily reached. Okay. So the final comment is that since you have to advocate for quantum phenomena to reach that state will be the typical time to reach that state is the typical time of the evaporation of a black hole, 10 to the 70 years or longer. If the expansion was enough, it would have been 100 billion years. And the lifetime of the universe would have been much, much shorter. So let's say that you need 10 to the 70 years to reach that state or more, the state I'm advocating for. And so the history of the universe is the history you know from primordial universe to a very short parenthesis where you have some interesting dynamics, including life, probably tens of billions of years, not more. And then no matter what, whether it is this, whether it is a leopard spot pattern of black dwarfs or clusters, etc., but basically the universe is doomed anyway to end into a state of totally uninteresting dynamics, or no dynamics at all. Thank you.
Very good. Thank you very much. So we have time for questions.
I have a question regarding the purely virtual bound that you showed before. So as far as I understand, this bound refers to the anti-de Sitter or Friedman-Robinson-Walker background.
Anti-de Sitter?
As far as I understand, it refers to the Friedman-Robinson-Walker background. Yes. Is that correct? Okay. So my question is, how does the bound change if you change the background for other backgrounds?
Probably it does change. Yes, certainly it does change, but we have considered only this background because it is the realistic one. So we haven't studied other backgrounds. For example, including the curvature K is not that simple. So I don't know the answer. I just know that it has to change. Yes, it does depend on the background.
What about, for example, a black hole background? Do you have an idea how this could change?
No.
Okay.
Any other question? And may I ask you something then? Okay, what's your assumption for the age of t? Because, for instance, there could be, I mean, you know, there are models of so-called big rip that if you have super acceleration, so if h dot is positive, then the fate of the universe will become much more sooner.
I just need that this is finite and decreases with time and tends to zero when time goes to infinity. So this is the simplest example, but the assumptions are just this, and that d of t tends to zero for t going to infinity.
Is there any other question or comment? If not, let's thank the speaker again.